Seeing that I could say something and share something with you all. So it's a great honor once again to be here. And I apologize for the late start. But I hope you had a good breakfast and all that. Because this session is going to be mentally somewhat challenging. So I want you to try and come along with me. Once more, are you all comfortable with English? You're okay with English? Okay. You please feel free to raise your hands and ask me questions, or maybe we'll just save it to the end so that I can make progress. But if there's a really burning question, I'd like you to stop and say, look, I didn't understand this. Could you please explain? So the inspired talks are meant to be more general, and so while we can touch upon the research we do, it should not be a research talk. That's the format. But it is to actually expose you to various facets of science, research in particular, and hopefully motivate you to pursuing research in whatever you do. I mean, it's not important that you do only basic science. I'm not saying that. These days, the difference between basic and applied science has somewhat become fluid. We're talking a lot about fluids, and therefore, whatever area you go into, biological research, medicine, engineering, applied science, astronomy, keep up the aspect of research, because research and innovation is very important for the country. So with that, I hope these talks will give you a sense of that direction. Once again, raise your hand, ask me questions. So what I'm going to talk about is swimming. So how do we swim? How do bacteria swim? How do small insects swim? How do things actually move about when the swimming gets tougher? For example, if I were to... How many of you here are swimmers? Raise your hands, come on. It can't be that. Okay. So, quite a few. Should I speak in Kannada? It is a yes, no?
No.
Okay, I'll mix my language and speak, okay? So, since there's both yes. So, how do you actually swim? What you are doing is the following. You're actually using the third law of Newton, right? So you're pushing the water behind. Your momentum is what is propelling you forward. So when there's the force of action reaction is caused by the momentum thrust that you have, and you land up pushing the water behind, and so there's an action reaction pair that propels you forward, right? Similarly, so that's a statement of the action reaction. The third law of Newton, which says that for an action there's a equal and opposite reaction that is acting on the different body. Okay, so therefore when you're falling to the earth is falling towards you, right? But since the distance moved is extremely small, you feel that because the mass is so high, so therefore the resultant momentum change is smaller. But momentum is indeed conserved, so there is an action-reaction pair. When you push something hard, that something is pushing back at you with strength. So that's what governs the flight of birds, the movement of human beings in water, and so on and so forth. But if you think about that's a bit of bacteria there. This particular, I'm actually not sure what bacteria it is. That's a swimmer, and this is a bacteria. Okay. Did you notice the little flagella of the bacteria and the tubular structure? I'm not sure which bacteria this is. I just grabbed it off the internet. But so we'll talk about small swimmers today. Okay. Because I'm interested in my lab, as my friend here mentioned, I like doing tabletop experiments, small experiments that you can set up with some optics and so on. And what I want to impress upon you is that there are really open and fundamental questions we can ask with very simple things. Okay? Science need not be about building large and expensive things. You can, with small things, it's important to ask the correct question. Okay? So this is not a new question, and many people have talked about this. So I'm going to show you an optical trap that we have built, and we'll trap these bacteria and then arrest their motion so that we can measure a few things about them. Okay? So that's how we go. So let's see. Watch closely. That's Mr. Oliver, the fish. He's a toy fish. You can buy these in China, or you can pick them off the shelves these days. So that's how Oliver moves. Now let's see how Oliver moves as the medium gets more viscous. Can't move, right? So what's Oliver doing? Oliver's moving his tail back and forth rapidly, and therefore pushing the water behind. That's propelling Oliver forward. So what's happening? So how do physicists understand anything? They understand things through building quantifiable relationships between physical quantities. Okay? So this is the normal process in which a physicist tries to understand nature. So we'll define something, and there will be a little mathematics here and there. You'll have to bear with it. Okay? Stop me if you didn't really understand something. So what I'll do is I'll define something called the Reynolds number. And the Reynolds number is simply the ratio of the inertial term as a result of pushing the fluid behind. What happens when you do this? You're using your inertia, mass times acceleration is called the inertia term. And what that does is it displaces the liquid. So the liquid is displaced by what is called an inertial force. But when that liquid is displaced, the surrounding liquid, so if you think of this liquid as a little pocket or a little envelope that's being displaced, the surrounding liquid is obstructing that displacement because the whole fluid is viscous. Or when you try and move in a viscous solution, you're not just propelling yourself. There's also the frictional force due to the liquid, and that's a viscous force. Okay? This way not to be true. For example, if a bullet is flying in, actually even for a bullet flying in air, this is true that for the bullet, although it can overcome the viscosity of the air somewhat, there is still a viscous drag on the bullet. So if someone is actually trying to predict the range and the target accuracy, they'll have to take into account the frictional forces due to the surrounding medium, and that's called the viscosity. Okay? And so if you divide the inertial force by the viscous force, you get a number. So this is dimensionless. You can work this out. Viscosity is in Pascal second in SI units. V will be in meters per second. A is the typical size of the object that you are discussing, and rho is the density of the fluid. So that turns out to be a dimensionless number called the Reynolds number. So if you have high Reynolds number, that means inertia dominates, as in the case of your swimming. If you have low Reynolds number, you're just trying to move and nothing's happening. Okay, viscosity is dominating. So for Mr. Oliver in the tub of the fluid, is a low Reynolds number swimmer, but Mr. Oliver in the tub of water, he is a high Reynolds number swimmer. Again, Oliver's inertial force has to become larger so that he maintains the high Reynolds number swimming. Okay? So, having said that, so these are the things we'll cover. So I'll show you how they behave in optical traps. And if there's time, we'll also look at, I also work with biological cells. I see how we can squeeze cells and so on using just optical forces. And I'll show you why it's related to the optics. So these are a couple of slides which I pulled off from an extremely important paper. See, some of these physicists, have you heard of the physicist Richard Feynman? Feynman had a wonderful way of, he was a brilliant researcher, but he had extremely nice ways of explaining things to people, especially to younger students like you. And for those of you who want to really get inspired by physics, there's a 3-volume lecture series of Feynman, downloadable on the internet. So I won't tell you, I didn't tell you this. It's called the Feynman Lectures in Physics, and it would be perhaps adequate at the BSc level, but although some of you are already exposed to calculus and so on, I strongly urge you to start, or you will be learning calculus soon. Okay, so this is a good time to actually go through them, especially volume 1. It's a wonderful way of explaining how things work in the language of physics. So anyway, like Feynman, there's this guy called Purcell who was also at the University of California at Berkeley, and this is all from an evening talk he gave. Just imagine, before a nice dinner you talk about bacteria and so on. So I just grabbed them off from that. So here he defines the Reynolds number, but what you can do is you can divide the fluid viscosity by the density and define something called the kinematic viscosity, okay? Which is the nu here. So AB over nu turns out to be, we'll work in CGS units here because that's a smaller number that you get. It's about 100th of a square centimeter per second, okay? That's the kinematic viscosity for water. And it's 1 centipoise is the dynamic viscosity, okay? So actually, if you take the fluid viscosity and divide it square and divide it by the density, you get a force, which means that you can estimate the forces involved in such motion. So if you take a high Reynolds number, or if you, for example, if you take a Reynolds number of 1, the force required to tow something of Reynolds number 1 is only about 10 to the minus 4 dynes. That's actually a very small force, which means that you give me any object, give me a submarine in water, and so a submarine, the typical A, which is the size of the submarine, would be very large. So for the Reynolds number to be around, to scale around R1, you have to have that V to be very small. So if you want to tow a submarine with Reynolds number 1, it's possible. You can just do that because you have to apply a very small force. And that's the whole game about having Reynolds numbers, keeping the Reynolds number to be low, okay? So there's a few typical Reynolds numbers there. So a swimmer swims by his inertia, high Reynolds number. Fish, somewhat compromised. Bacteria, they're really in big trouble, man. Bad swimmers. Why? They're swimming in a low Reynolds number environment. Water itself is bad enough. Why is that? Because the inertial term corresponding to the bacteria is very small. Okay, so the viscous dominance. Whereas if you guys try to swim in molasses, anyone know what molasses is? It's a byproduct of making, it's one step before it happens to become sugar, right? So that's highly viscous. So try swimming in there, you can't. So if you calculate how much a bacteria swims, just remember this because there's a small calculation I'd like to show you. I'd like to show you that why, despite being a low Reynolds number swimmer, a bacteria is an efficient forager for food. He need not do much. The food just comes to him. I'll show you that. Through simple physics calculations. That's the whole point. You can use physics to understand by just putting in dimensions and so on. So here's a typical distance simply by the lower Reynolds number thing. So if you give a push, it goes ballistically, that is without the viscosity interfering, for about 1/10 of an angstrom. That's like less than the size of an atom, right? 1/10 of the size of an atom. And it does so in a time of about 3 times 10 to the minus 1 microseconds. Okay, so that's micron seconds. Okay, so all right. Now as an equation, which you'll have to bear with me a little, because this is the key point to illustrate what I'm going to say. Anyone recognize this equation? Some of you who may have done a little advanced. That's called, this is the equation that governs any movement in any fluid. Give me any damn fluid which has slow movement, fast movement, turbulence. Everything is governed by an equation called the Navier-Stokes equation. Okay? The Navier-Stokes equation simply is a conservation equation. It tells you that if a body is moving in a fluid, there is a change in the fluid pressure gradient, and the change is compensated by the inertial term, something that's pushing the fluid back, and the fluid itself being displaced as a result of that. So these are both inertial terms. So if you actually go back, and I'll give this as an exercise, if you can rewrite those terms in terms of this Reynolds number. So put in the Reynolds number definition, do the divisions, and you'll get the right hand side in terms of the Reynolds number. Notice in this equation there's a time dependence. Okay? So that's delta P, the change in the pressure. That's the viscosity. So that's a viscous term. Okay, that's a viscous term that's holding this displacement of the fluid back. So that accounts for everything. The point is, it's very difficult to solve this. By the way, I've written this in a non-calculus language. There should actually be some things called curls and gradients and all that. You'll learn that when you go to advanced calculus. Let's not worry about that. Dimensionally, this is correct. Okay? So, low Reynolds number means what? Inertia doesn't dominate. So, we simply make the right hand side equal to 0. What does that tell you now? It tells you that there is no time dependence in your equation in a low Reynolds number regime. The change in pressure is compensated by the viscous drag. Okay? Something's really trying to move hard, the viscous drag is preventing it. That's so only these two terms. So then how the hell do low Reynolds number things move? Okay, that's the next part of the question. Time dependence absent. So, Purcell, the guy whom I'm talking about, who has made all these nice sketches, wrote a paper called Life in the Low Reynolds Number Regime. And in this paper, he invented a small theorem called the scallop theorem. Okay? You know what scallops are? What are scallops? Chipmino. Some of you. Okay. So this is that shellfish which you call. It has some fleshy inside and it has a shell. Okay. I think it's also called clams. I think people call them clams. Or maybe scallops and clams are slightly different. But there's a theorem after this little humble creature called the scallop theorem. What it says is the following, pay attention. If you have a low Reynolds number swimmer, you can't swim if you have only one hinge supporting you. In other words, if the scallop were to do, scallop ಏನು ಮಾಡುತ್ತೆ? ಬಾಯಿ ಕಳಚುತ್ತೆ, ಬಾಯಿ ಮುಚ್ಚುತ್ತೆ. ಬಾಯಿ ಕಳಚುತ್ತೆ, ಬಾಯಿ ಮುಚ್ಚುತ್ತೆ. When the scallop opens its mouth, the water rushes in. Yeah? So what does that mean? It goes backward. When the scallop closes its mouth, it goes backward. When the scallop opens its mouth, it comes forward. No net movement. No time dependence in the equation. No net movement. So, the scallop can't swim. Right? Wrong. It does swim. I'll show you how it does later. But if the scallop were to be doing simply this, slowly, it's not going to swim. You have to have in your equation something that is not time reversible. Time dependence hoitu andre ಏನು ಅರ್ಥ? Navier-Stokes equation. That means that there's no question of time there. So it's perfectly time reversible. It's a time reversible equation. There's no time figuring in it. Whereas you have to get some time reversibility na violate ಮಾಡಂತ ಒಂದು ಮೂವ್ಮೆಂಟ್ ಬೇಕು. ಎರಡು ಹಿಂಜ್ ಇದೆ ಅಂತ ಇಟ್ಕೊಳ್ಳಿ. ನಾನೇ ಒಂದು ಸ್ವಿಮ್ಮರ್. I'm a swimmer. Okay? So let's see how I'll swim. I start that way and I come that way. Okay? I come that way. 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 Okay? I'm pushing the fluid. Now that's not strictly time reversible because if I started that way, I come that way. I come that way. The next step is that. Okay? Not that. So, I've broken the time reversibility in my sequence of steps. So, suppose I plot this theta 1 and theta 2 in terms of the positions in my, I can plot it then in what I call the configuration space. I make theta 1. So when theta 1 is changing, theta 2 is constant. So I plot it, I get actually a square line. What would I get for the scallop? I'll simply get for the scallop a straight line which is translating back and forth. Therefore, time reversible and therefore no movement. Here, not time reversible in this. So, the idea is that you need at least 2 hinges to swim. You need at least one hinge iddalli ಈಜು ಸಾಧ್ಯ ಇಲ್ಲ. That's the scallop theorem. Okay? Simply a consequence of the Reynolds, the low Reynolds number. Therefore, time-dependent terms, inertial terms are thrown out in the Navier-Stokes equation. What about that rotator? Can someone figure out how that may rotate? Does that rotate? It does. It does by distortions. He's just imagining all kinds of swimmers. ಸ್ವಲ್ಪ compress ಆಗಂತ ಒಂದು ಪ್ರಾಣಿ ಇದೆ ಅಂತ ಇಟ್ಕೊಳ್ಳಿ in your water, and that is going to start tumbling. But when it tumbles, it compresses itself in a way. So when it goes back, that compression is not repeated. Okay? So that each tumbling sequence, it is not time reversible coming back, because when it comes back it doesn't compress the same way. So therefore some twist in the time reversibility sequence has been changed. So a distorting turner is going to be able to propel forward. Now imagine this distortion in 3 dimensions. What are you doing? You're propelling yourself forward. Okay? Because that's not possible. Because the distortions are not the same way in when it's coming back. So, you've broken time reversible symmetry. That's a possible solution. That's like your little fish there. Actually, what you did not notice in the fish, that little Oliver swimming, is if the tail, coming back to the scallop theorem, if my tail were rigid, and I'm just doing that, no swimming, no. Why? This is exactly reversible to that. But if my tail were not rigid, if it starts bending one way, slight bending because of the water pressure, the plastic is flexible and it bends the other way when it goes that way. Time reversible or not? Yes or no? Not. Because E kade hodaga bending E tara aitu. E kade hodaga bending E tara aitu. It's not the same. One has bent to the right, one has bent to. You've broken the time reversible symmetry, you can move. So that Oliver that was doing that was slightly bending. That's why if you take a rigid oar and you keep doing that, your boat is not going to move. The oar has to be a little flexible. A little flexible. Then you'll start moving. Very interesting consequences of when the Reynolds number involved is low. That's the point. What about in a corkscrew? We are coming to the final bit. What about in a corkscrew? You know what a corkscrew is? Wine bottle open madake. Hige. Or any, if you have a cork, what's happening? Again, not time reversible. Because if you trace any path back, it doesn't move the same way as in the front. So, what do bacteria do? They use exactly this principle to move. Does a scallop swim? Let's see. Oops. Someone's going to try and touch it. It swam. It did not swim the way you thought it will swim, right? You thought it will swim that way. It's swimming actually this way. What is it doing? Is it a high or a low Reynolds number? It has to overcome the Reynolds number somewhat, no? It's not just passively doing that. It won't move. Why is it? So what's happening? And it's moving forward. How's it moving? Any guess? Someone? It's moving in the direction it's opening, right? So what's going on? It's squirting the water from the sides. The front of the mouth gets closed. There are something called adductor muscles. Those muscles actually prevent the water from escaping. So it opens, the water comes in. It closes, the water doesn't go out from the front, it goes out from the side. So it creates two jet streams. It better swim. If it's not a swimmer in salt water, some big fish is going to come and eat it. They are all living beings are designed to escape the vicissitudes of evolution and the environment. Okay, so they are always trying to overcome some predator. So the scallop does move, but not according to the scallop theorem. So bacteria do similarly. It's now discovered that they actually have a little rotor which is free to move. So if you look at the bacterial body, there's a basal body there, and attached to that is a hook with a curved filament. So what's happening is when the bacteria propels itself forward, your filaments are moving, they are rotating, but they are also twisting up. They are actually getting entangled. When they get entangled, they have to unbundle. So when they unbundle, what happens? The bacteria loses its initial direction of rotation, of movement. That's called tumbling. So bacteria typically do a jerky 30 microns per second speed as we calculated, and they move a very short distance. They tumble, they move, they tumble, they move, they tumble. So that's how they move, and they do this with the help of what is called the flagella. We'll skip this, but I just want to show you that when they move, they consume their efficiency of propulsion. We can calculate that. I'll help you with that if you have some time later. It's only about 1%. They're doing all this, and for the nutritional intake and the output efficiency, kevala 1% matra. So with such a low efficiency, what the hell is going on again? Why are they such low efficiency swimmers, yet they don't suffer for food intake? Let's see if that. So if you work this out, it turns out to be that they're consuming about half a watt per kilogram of their weight, as opposed to cars and buses, which are several orders of magnitude higher per kilogram. Okay, so they are low energy consumers, so it doesn't matter if their propulsion is small. Before we understand what this is all about, let's try and give some homage to this man. Who's he? No prizes for guessing. Is probably the most famous icon on all t-shirts and so on. So Einstein, in the year 1905, did 3 important papers. It's called the miracle year. Why are you smiling? I know why she's smiling. She has a little. But yeah, some people call me because of my long hair. But it's only the appearance, nothing else. Anyway, so no, that's an early Einstein. He looks better. But the later Einsteins are all quite unkempt. So Einstein actually published at a ripe old age of 27. He published 3 papers, and all of them revolutionized physics. Right? So, can you tell me what are those 3 papers? Please. Sit down and answer.
One was the theory of relativity.
Yeah.
And the second one was photoelectric effect.
That's right.
And then the third one was on Brownian motion.
Very nice. So, the theory of relativity revolutionized how we think of space-time. So, space and time were no longer separate. They were one entity. And a wonderful conception that nothing can be said to be simultaneous. It is related by the space-time separation. One day so that the photoelectric effect gave rise to, the explanation for the photoelectric effect gave rise to this whole edifice called quantum mechanics, on which everything is based. Everything in this universe is quantum mechanical, ultimately. And the third one was on what we are talking about, Brownian motion. In fact, this is his most cited paper. Okay, and his PhD was on Brownian motion, by the way. He became Dr. Einstein by looking at Brownian motion. So what is Brownian motion? Here's a 10-minute little lesson, and we'll stop. So you may have done this experiment, right? If you actually put little globules of fat, you take some milk, ಹಾಲನ್ನ ತಗೊಳ್ಳಿ, ನೀರಲ್ಲಿ dilute ಮಾಡಿ, microscope ಕೆಳಗೆ ನೋಡಿ. What happens? You see that those globules of fat, which are a few microns in size, exhibit zigzag motion under a microscope. So I'll show you a cartoon which will give you a hint on what's going on there. That's a cartoon of what I call Brownian motion. And the next one is a real videogram of some particles. These are typically 2 to 3 micron size in a truck. So this is something where those particles correspond to that blue thing there. What are the little red smaller objects in the cartoon? Andre, ನೀವು microscope ಕೆಳಗಿಟ್ಟು ನೋಡಿದಾಗ the big object seems to be moving around randomly. I'll show you some real video of Brownian motion that I recorded later. That shows random movement, okay? But you don't see the little red objects there. What are those? Why does... Actually, when Brown saw this, he did this experiment with pollen grain. And he thought that it was because the pollen grain was live, that it had life, therefore something called a living force, so it's propelling itself randomly. Then he killed the pollen grain by putting it in boiling water. He put it back in the liquid and again it was showing random movement. Why does it show random movement? Again, hucha. Come, make a guess. See, one thing as students of science is you should always be questioning. You should keep questioning. You should say, why is that happening? What is the knowledge basis I have? Can I explain it in terms of what I already know? Or is there something new that I have to postulate? That's the process of science. So, do that exercise. What do you think is happening? Why is this thing getting jostled around? Because something is pushing it, right? Something is pushing it randomly. What's pushing it? It's a 3 micron, let's say 1 micron size. Because if it was smaller, if it was a nanoparticle, you can't see it in water. So it has to be slightly bigger so that you can see it in a microscope. Hogi Madi experiment. Put micron sized objects in, look at it in water, you'll see them actually moving in a kind of zigzag fashion. They don't just sit there in the water. That's called Brownian motion. Why is it happening? What is water? What is water made of? I want to hear that critical word. Everything in the world is made of atoms, yeah, but for water it's molecules, right? Those molecules can be broken up into atoms, but what's pushing around this little bead there are the molecules. The molecules of it. Brownian motion was the first proof of the existence of molecules, because if matter were actually continuous, as people believed in the 19th century, nammalli gottittu anu anta kariyodu. Discrete property of matter was already postulated, although it was not experimentally verified. It's the experiments related to Brownian motion where you could calculate the Avogadro number exactly. That is what led to the proof of molecules, the existence of molecules. Why are they moving randomly? Because the molecules are in a heat bath. This is not at temperature T equal to 0, absolute 0. It's at 300 Kelvin or about 27 degrees Celsius. So the molecules are thermally agitated and they are coming and hitting the bead. The momentum imparted to the bead is making them move around randomly. So tell me now, among the swimmers, going back to the swimmers, is this suffering Brownian motion more, or is the low Reynolds number guy suffering Brownian motion more? The low Reynolds. Very good. So you can figure this out yourself. So your bacteria are moving under extremely difficult environment. Band molecules vardita ide bacteria. Adannella ತಪ್ಪಿಸ್ಕೊಂಡಿದ್ದು ಮುಂದೆ ಹೋಗಕ್ಕೆ. So what can we say about the Brownian motion? Let's do another little ಇನ್ನೊಂದು 10 ನಿಮಿಷ. Then we'll stop. Okay, let me ask you this question. Suppose I were a Brownian mover. ನಾನು Brownian ಅಂತ ಇಟ್ಕೊಳ್ಳಿ. ನನ್ನ ಪ್ರಪಂಚ ಬರೀ ಒಂದೇ ಡೈಮೆನ್ಷನ್ಗೆ ಸೀಮಿತವಾದ್ದು. ಅದನ್ನು ಫಿಸಿಸಿಸ್ಟ್ ಯಾವಾಗಲೂ ಮಾಡ್ತಾರೆ ಇದು. If you have 3 or 4 dimensions, what they do is they simplify. They say ಎಲ್ಲ ದಿಕ್ಕುಗಳು ಹೇಗೂ ಒಂದೇ ದಿಕ್ಕಲ್ಲಿ ನಾವು ಇದರ ಮೋಷನ್ ಅನಲೈಸ್ ಮಾಡೋದು, ಆಮೇಲೆ 3 ದಿಕ್ಕಿಗೆ ಅದನ್ನ ಜನರಲೈಸ್ ಮಾಡೋದು. ಓಕೆ, so if I were a Brownian mover and I'm doing that randomly, I'm getting 1 kick, 2 kicks, 1 kick, 3 kicks randomly. So if I build the statistics of all the kicks versus the displacement, say from the mean position, where will be the highest probability? Suppose I start from here, I'm kicked, I'm kicked, I'm kicked, I'm kicked. So each of them is a displacement. So I plot on the x-axis displacements, positive, negative, versus probability of being at that step. Which will have the highest probability? At the center, away from the center? At the center. ಯಾಕಂದ್ರೆ random ಆದ್ರಿಂದ ಈ ಕಡೆನೂ ಹೋಗ್ಬೋದು ಆ ಕಡೆನೂ ಹೋಗ್ಬೋದು. So if I calculate the average displacement, what will it be? Average. I'm taking the positive, negative, I'm summing them all up and dividing by the number of displacements. 0. The average, so a Brownian particle on an average has been displaced 0 because it's completely random. So what you don't look for is the average. You look for the square of the displacement so that you are taking away all the negative displacements and then take the square and average it, which is what Einstein did. And that's my little Brownian particle. That's it. So that's your one-dimensional, not quite one-dimensional, but that's okay. So I'm taking all the displacements. Of course, in this figure, these are vectors. I'm squaring. I'm doing v dot product. Gotta? Okay. V dot v is a scalar. Okay, that's v squared, or L dot L in this case is L squared, and that stands for average. And what Einstein predicted was that the average square of the displacement is simply proportional to the time. Andre, if you observe it for long enough, it will have moved. Ishte helta iddidam. Okay? Big deal. There's actually a very big deal. He showed that the proportionality constant is called the diffusion constant. That's very important, because if you do this experiment, plot on a log-log scale, the slope of your plot will give you the diffusion constant of the material. Which means if it's highly viscous, so ನಾನು ಹಾಲು ಮತ್ತೆ ನೀರು ತಗೋತೀನಿ, ಸೇಮ್ ಬ್ರೌನಿಯನ್ ಪಾರ್ಟಿಕಲ್ ನ ಇಡ್ತೀನಿ, ಸೇಮ್ ಟೈಮ್ಗೆ ಮೆಷರ್ ಮಾಡ್ತೀನಿ, ಯಾವ್ದು ಹೆಚ್ಚು ಮೀನ್ ಸ್ಕ್ವೇರ್ ಡಿಸ್ಪ್ಲೇಸ್ಮೆಂಟ್ ಇರುತ್ತೆ? ಹಾಲಲ್ಲ ನೀರಲ್ಲ. ಅದಕ್ಕೆ ಈ ಈಕ್ವೇಶನ್ ಬೇಕಾಗಿಲ್ಲ, ನಮ್ಮ ಅಜ್ಜಿನೂ ಹೇಳ್ತಾರೆ ಹಾಲಲ್ಲಿ ಅದು ನೀರಲ್ಲಿ ತಾನೆ. Because the diffusivity in water is higher, which means the viscosity is lower. So the diffusion constant has to be inversely related to the viscosity. That you can figure out, and indeed it is. Okay? So let's keep this diffusion constant. If you work it out, it turns out to be about 10 to the minus 5 centimeters squared per second for a bacteria. So now let's figure out, let's come back to our moving bacteria. So suppose how can a bacteria search for food? One is, it can simply suffer diffusion. But if it does that, suppose the food is in a particular direction, random kicks are not going to assure that it's going to go to the food. Or ಸ್ವಲ್ಪ ಕಲ್ಸಕ್ಕೆ ನೋಡುತ್ತೆ ಅಂತ ಇಟ್ಕೊಳ್ಳಿ, it's going to stir. Stir means it's going to displace the object by a certain distance. So let us see, suppose it stirs. So over a typical length scale of the bacteria L, for a velocity v, the time for stirring is say L by v. Whereas if it were purely diffusing, the time for diffusion is L squared by d. So suppose the bacteria were to think, ನಾನು ಸ್ವಲ್ಪ ಕಲಿಸ್ಬಿಟ್ಟು ಅದನ್ನ ಹತ್ರ ತರಿಸ್ಕೊತೀನಿ ಅಂದ್ರೆ, that means the time for stirring should be less than the time taken over diffusion. Okay? So if you do that, if you divide this by that, you'll get some number which is LV over D, which should be much greater than 1. But if you calculate for typical values of the diffusion constant, V was 30 microns per second and L is a few microns, you get about 10 to the minus 5 centimeters squared per second. Whereas the Reynolds number corresponding to the kinematic viscosity is much higher, which means Papa bacteria kalsagrinda yenu prayojana illa. Okay? It might as well just suffer diffusion. So we should see, array, idu bari diffuse aagta idre, is it getting any food at all? So how do we estimate how much food is gathered? Suppose you assume the bacteria to be a spherical sphere, okay? So if it is a spherical sphere diffusing, okay? It's diffusing, but say there are nutrient molecules all over the bacteria. So it's surrounded by nutrient molecules. You can estimate the rate of food supply. It will simply be 4 pi times the radius of the bacteria for a spherical bacteria times the diffusion constant times the nutrient constant. That is the amount of nutritional molecules per volume. Actually put this in a dimension and you will see that you will get number per second. Okay, 4 pi is a number, A is a length, N is 1 by length cube, so there is a 1 by length squared, and this is a length squared over second, so 1 by second. You will get the number of molecules per second. So if it wants to increase the food, so if it's simply diffusing, the food supply rate will be 4 pi A N D molecules per second. Now suppose the bacteria says, illa naan channagi tinbeku andre, it will have to increase its velocity to 700 microns per second. Even a 1% efficiency swimmer, it swims only at 30 microns per second. So propulsion is not going to help the bacteria anyway. That's a very surprising answer. So the bacteria might as well just diffuse. It need not even try to propel itself. It will be able to eat food at 1% efficiency of its moving. It's okay. But it still moves. It still moves because evolution has taught it to move. In the sense that if it were to be just sitting there, it's going to be passively diffusing. It might as well try and change its position because passive diffusion is not going to get it nearer to the food molecule. So it tries to outswim the diffusion. It outswims the diffusion just enough. So if you calculate that length, it turns out to be 30 microns. So when the bacteria is propelling at 30 microns per second, in a second, it's gone about 30 microns, which is just enough to get rid of the diffusion kicks. So nature hege design madide andre, the bacteria is moving just enough for it to overcome diffusion. There's no point in it moving faster because its energy cost is going to be extremely great. Okay, so this is how the bacteria moves. Since we are running out of time, I'll really hurry through the last part. 5 minutes. 5 minutes. How do we actually understand all this? Question. So watch this closely. Now this is a real video of Brownian motion, but I want you to watch 2 beads there. These are all well prepared latex polystyrene beads of about 3 micron length. So just watch this video. Those are Brownian. Watch that. Watch that. So what happened? I switched on a laser beam and I actually trapped one of the Brownian beads, okay, and then another Brownian bead swam into that trap, and so two Brownian beads got arrested. What I've created is something called a laser trap. A laser trap, it's also called an optical tweezer, and it's very easy to build these tweezers. It doesn't cost a whole lot of money. If you look at most undergraduate science experiments in the US, they all build tweezers, and you can do very nice little experiments with tweezers. Basically, a tweezer is, so what we are doing is we are looking at things that are happening at a length scale much thinner than the size of your hair, okay, the width of your hair. So that's light thinner. So an optical tweezer, don't worry about this, is essentially a tightly focused laser beam. The tightly focused laser beam creates a force on the beads called optical gradient force, okay, because of the distribution of power across the beam of a laser. So it works somewhat like this. Think of that as the tightly focused laser beam. So I put a Brownian bead in the center, it gets trapped at the center. So if the molecules come and try and kick the bead out of the trapped center, the optical gradient force holds it back. If it actually pulls it too much, it pushes it. If it pushes it too much, it pulls it. Where do you see such a behavior? You see that in a spring. So an exact harmonic spring is something where the force is proportional to the displacement. So similarly for an optically trapped bead, it will be for small displacements, the optical trap will behave like a spring. So that if you measure the spring constant, that is the force per unit displacement, you get the strength with which your optically trapped bead is held. So we measure those strengths for a trapped bacteria to see, don't worry about this, you can create two optical traps. Here I'll show you an interesting video. This is the inverse problem. Okay. No, never mind. I'll just skip this video. Okay, let's see if this works. What are those? These are freely swimming bacteria. See that one? What are those? Those are two trapped bacteria. So they are trapped in the optical trap. So what are they doing? Their flagella is beating. So they have only 1 degree of freedom now. They are trapped here. They are long chain bacteria. They are trapped at one edge. They are doing it. That's the only degree of freedom they have to move. So we look at the rotation speed and figure out the propulsion rates. Okay? How we do that is a detail which I will skip here. But what my student in the lab is trying to do is to get the swimming efficiency of various bacteria. There's a reason we are doing it. We are doing this because we want to design artificial swimmers. The next level of nanotechnology is where you can actually take an artificial swimmer, attach a drug molecule to the artificial swimmer, and have directed motion. Suppose your body is like a fluid, okay, the blood is a fluid. You have these swimmers get directed and attached to particular cells. So you don't waste your drugs. You actually use these nano swimmers with cargo on their backs to zone in to the target molecule that you want. So it's important to understand how do swimmers swim and how do they do this in low Reynolds number regimes. Okay, so that's really. Thank you very much for your attention. Marathi, I know Hindi, so I may be able to understand a little, but I'll answer back in English. Yeah.
So when bacteria move in a blood.
When they move in blood, yeah.
So then is it the force, the heart pumps the blood, so there's a speed. So the bacteria just move with the speed or they have their own movement?
Very nice. Extreme. In fact, this is a question that is very difficult to answer, because this is no longer, it's actually turbulent flow. What's happening is each time your heart does that, the blood rushes not laminarly. In certain microchannels, it becomes turbulent. Okay? In turbulent flows, there's some problem with this Reynolds number analysis. Nonetheless, just to answer the bacteria does, because finally it goes and invades some, so it does actually overcome that turbulence. It is subjected to the heart pump flow, but it overcomes that. So presumably these bacteria are highly energy efficient. Okay, so they are trying to overcome the pump speed and the turbulence induced around their body thereof. So very good question. So if you are a nanobio engineer, these are the central problems when you are addressing. So therefore it's very important for you to first understand the fundamentals. What's the Reynolds number? How does that govern motion? What happens to the Reynolds number in situations where there's turbulence? Andre ನೀವು ಆ ನೀರನ್ನೇ ಭಾರಿ ಸ್ಪೀಡ್ ಮಾಡ್ತೀರಾ ಅಂತ ಇಟ್ಕೊಳ್ಳಿ. Do another experiment. Do all this in a put a pipe, attach a motor or a pump to one end, keep pumping at a regular speed. Try and see what happens to your Brownian motion locally. Put a microscope. You can do wonderful. You can do 1,000 kinds of experiments. They all lead to very profound insights into the world of nanobio. And these are all applications in nanobiomedicine. But behind that, very fundamental questions. So you should keep the question sharp. You should always keep your question very sharp. Okay? And then you may arrive at an answer. May. ಯಾವಾಗಲೂ ಉತ್ತರ ಸಿಗುತ್ತೆ ಅಂತ ಹೇಳಲಿಕ್ಕೆ ಬರೋಲ್ಲ. Any girls? You're all being nodding your heads, but you're not asking a question. Please don't hesitate. I don't know everything. I know some things, and actually did a lot of homework for this, because this person's papers, by the way, I can give you the reference. These are all available on the internet. It's a very brilliant paper. Try and read it. You may be able to understand it. It's from 1977 actually. He gave an early talk. Of course, we have progressed much more on bacterial movement. But at the time, Purcell arrived at some very correct answers simply by estimations. See, physics ಅಲ್ಲಿ ಇದೊಂದು ಬಹಳ ಒಳ್ಳೆ ಕಲೆ ಇದು. ನೀವು ತೀರಾ ದೊಡ್ಡ ಈಕ್ವೇಶನ್ ಸಾಲ್ವ್ ಮಾಡೋ ಅಗತ್ಯ ಇಲ್ಲ. ಸರಿ, ಸುಮ್ಮನೆ ಅಂದಾಜು ನಂಬರ್ಸ್ ಹಾಕಿ you can get dimensionally, or you can figure out what's going on roughly. And that's a very good art to develop and practice in physics. You need not always get the whole formula. Right? You may be off by a factor of 2 or 5, it doesn't matter. So these are called back of the envelope calculations. Andre ಒಂದು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಪ್ಪ ಅಂದ್ರೆ ನೀವು ಒಂದು ಪೇಪರ್ ಇಟ್ಕೊಂಡು ಹೀಗೆ ಅಂದಾಜು ಮಾಡಿ ಹೇಳ್ತೀರಲ್ಲ, ಯಾವುದೋ ಒಂದು ಎನ್ವೆಲೋಪ್ ಸಿಕ್ಕರೆ ಆಗ್ಲಿಕ್ಕೆ. So it's called back of the envelope. So you should learn how to do back of the envelope calculations. Ask your teachers to teach you that. Very useful. ನಾ ಹೆಚ್ಚು ಕಮ್ಮಿ ಎಲ್ಲ ಮಾಡೋದು back of the envelope calculation. Okay, if there are no other questions, I thank you once again for